Good day, I'm Norman Wahlberger, and today we start an exciting new chapter in this course on the foundations of mathematics, where we start to delve into the problems that currently exist in modern pure mathematics. There are very serious logical difficulties that are generally unacknowledged by the profession, but which seriously undermine both the education of young people and the research endeavors of us pure mathematicians. So this second part of the course follows from the first part. In the first part, we've had a pretty good look at the three core subjects in mathematics, which are arithmetic, geometry, and algebra. And I've rather slowly and methodically prepared a pretty decent foundation for those three subjects. We're now heading towards analysis, calculus if you like, and set theory, and then some higher subjects as well. But unfortunately now we're bumping into the mathematics which is already there, which is, in my opinion, deeply flawed. So I have to clear some space, and I have to try to reorganize your understanding of modern mathematics. That's what I'm going to be trying to do in this second part. So I'm thinking of it as actually being like a trial. This is mathematics on trial. And I'm going to try to demonstrate why it is that modern pure mathematics doesn't really work. Logically. It of course works on a lot of other levels. It works as a sociological enterprise. There's thousands of practitioners, thousands of papers every year, conferences, seminars, students graduating, and so on. So at that level, it works. But at the level of a logical discipline, it doesn't work. And that's what I'm going to have to try to convince you of. So I see myself as something of a public prosecutor on behalf of the people, by which we can generally mean students, present and future. And my job is to clearly lay out what the difficulties are and to challenge the professoriate to meet and acknowledge those difficulties. So we'll see how we go. I'm going to be concentrating on 5 key problems. And in the course of these lectures, and we're going to be going on for quite some time, I'm going to try to convince you that modern mathematics is characterized by, first of all, inconsistent rigor. The level of rigor is not what it should be, and the rigor that we do see is inconsistent, which allows all kinds of strange arguments and weak arguments to flourish. Problematic definitions. So many definitions of modern pure mathematics, when you look carefully at them, start to disintegrate. I'm going to demonstrate that claim. I'm going to talk about the reliance on axioms, which characterizes 20th century mathematics, which is a deeply unfortunate development, contrary to the historical trend up till that time, and is, in my opinion, a reversal of direction. Actually ended up making us go in the wrong direction rather than the right direction. So we'll have a very careful look at that, very important. Modern mathematics, because it's essentially off the rails logically, it turns out to be computationally much weaker than it ought to be. There are many situations where we have these overblown theories in which, when you actually try to compute important things, you find yourself stymied. So the theories are big on talk and big on abstractions, but when it comes to computing stuff, then we see that things are not as rosy as they ought to be. And finally, the lack of proper rich source of examples in many modern mathematical theories. This is a key litmus test to whether you're understanding mathematics correctly. If you're understanding mathematics correctly, there are a lot of rich examples that you can lay out very clearly and people can have a look at. That's like scientific evidence. And when you have theories with a lot of theorems but very few or inaccessible examples, it's a sign that there is something wrong. And in modern mathematics, unfortunately, there is a very lot that is wrong. And I'm going to try to demonstrate these things. So I need to make some important clarification with my charges. My charges do not apply across the board, and they do not apply uniformly. There are some branches of mathematics which are a lot more guilty of obscure logic than others. So let's have a look at what I consider to be the problematic areas and the non-problematic areas. The problematic areas, first of all, include prominently calculus and analysis, set theory and logic, modern geometry and topology, probability theory, measure theory, and to a certain extent algebraic geometry. So I'm going to try to convince you or show you examples of how these subjects are all fraught with logical problems. Very serious logical problems that are not easily fixed. So these subjects are going to really have to be completely rethought. It's a very big challenge, very serious challenge, and of course will be resisted strongly by the practitioners, who will do their utmost to try to prevent me from making this case successfully. There are also, however, non-problematic areas. And generally speaking, the more finite an area, the more concrete an area, the more down-to-earth an area it is, the less problematic it's likely to be. The star performer in modern mathematics, as far as logical clarity goes, is almost surely the subject combinatorics, which, not surprisingly, has really been a star performer in the last 50 years. In pure mathematics, in my opinion, it's been really the dominant subject in terms of its explosive development. And that's not a surprise, because I think people are subconsciously, at least, aware that combinatorics really makes sense. While a lot of these other subjects, it's a lot more dubious. Aspects of number theory are quite solid, but there are also aspects of number theory which are questionable. So I put a little question mark saying that not all is right in this subject, but a lot of it is. A lot of algebra is fine, but there are some aspects of it which need rethinking. Most of linear algebra, or at least a good part of linear algebra, is fine, but there are also some significant parts of that have to be rethought. There's aspects of algebraic geometry which are also fine, so it actually gets to be in both categories. And there's other subjects, for example, finite geometry might be put over here, although you might also say it's part of combinatorics. So I'm not making blanket across-the-board accusations here, but the accusations do extend over rather a large part of the subject. So many people will be affected, and many undergraduate courses are affected by these claims. And another important clarification that I need to make is that most of what I say applies to pure mathematics and not to applied mathematics. Applied mathematics is a very broad discipline, which for me at least includes statistics, computational mathematics, engineering mathematics, fluid mechanics, aspects of mathematical physics, aspects of computer science, and other things as well. Applied mathematics has had a great run in the 20th century, and probably it's fair to say that applied mathematics has dominated a lot of the developments of 20th century mathematics. And in my opinion, it's mostly all good. So what I'm saying does not apply to applied mathematics, which is concerned with concrete, objective goals and not so much with theoretical abstract understanding. However, there are some places where some of these applied subjects overlap with pure mathematics, and when they do, there is probably some difficulty in those subjects as well. One of the very important challenges for pure mathematics is to try to figure out mathematics in a way that's useful and powerful for applied mathematicians. And I claim that once we start getting our act together and figuring out how mathematics goes properly, then a lot of these disciplines will be strengthened immediately, because it's much easier to work with a proper mathematics than it is with an improper mathematics. Proper mathematics is almost always more powerful and insightful. The first key problem that was on my list was inconsistent rigor. And that might be a surprise to a lot of students of mathematics who have been trained to think that we are now at a high point as far as rigor goes in the history of mathematics. There is this story that accompanies the teaching of mathematics, which suggests strongly that rigor has been more or less going up in the last few hundred years. So here's a little diagram with time on this axis and rigor in this direction. And say here is a time of Euclid and here is now. And the general perception is something like this, that generally the level of rigor in mathematics at Euclid's time, as years went by, it went up and down a little bit, but in the last few hundred years it's been steadily increasing, and now we are pretty well at a high point, and rigor is becoming more and more solid and universal. This is a very unfortunate perception because it's almost the opposite of what is really the case. A much more accurate picture is this one here. The same axes, time and rigor. But in this more accurate picture, it's revealed that rigor has actually been, with some wobbles, decreasing pretty steadily since the time of Euclid. Rigor has not been increasing, especially in the last few hundred years. There's this common idea amongst analysts, and it's often propounded in books, that these days the modern analyst is much more rigorous than, say, Euler was. People look back on Euler and sort of in a superior way that Euler, he had some serious problems with rigor. Well, I'm going to show you that Euler was in fact much more rigorous in a reasonable sense of that term than most modern analysts. I'm going to make that case, and you might be surprised. Okay, so please have a think about this. Okay, I have to make this case, and I will make this case. But it's probably good that you see these graphs so that you have a sense that there are alternate perceptions, alternate possibilities to thinking about things other than the one that we have sort of been indoctrinated to believe in. So in this course, we've already established definitions for many simple mathematical objects, including natural numbers, first of all. That was our starting point. And then integers we defined, fractions, rational numbers, points, lines, area, triangle, parallelogram, quadrant, spread, circle, vector, polynumber, tangents, algebraic curves, and probably some other things too. These are concepts which can be defined clearly and precisely. And I've hopefully shown you how to do that, or at least one way of introducing those concepts clearly and precisely. However, there are a lot of modern pure maths definitions which are highly problematic, for which this statement is not at all so clear. For example, well, the definition of a function. We've talked about that definition and the problems associated with it in Math Foundations 42. If you haven't watched that video, have a look at it. I claim that the modern definition of a function doesn't work. And we're going to be looking at a lot of other modern definitions which currently don't work. When you look at them carefully, the logic breaks down, including the concepts of sequence, real number, limit, continuity, derivative, integral, or whether it's Riemann integral or Lebesgue integral, eigenvalue, infinite set, infinite group, actually infinite anything pretty well, manifold, topological space, variety, category, metric space, topological vector space, and many others. I claim that each one of these definitions currently is problematic and unfortunately not so easily fixed. You cannot just tweak the definition a little bit and bring it into focus. These definitions are all seriously and fundamentally flawed. And it's part of my job in the months ahead to go through examples and to show you exactly what is wrong with these definitions. So some of these concepts can be rescued, but most of them require a serious restructuring of the underlying theories. Now there will be many of you, especially those pure mathematicians who are watching, who are seriously going to challenge that statement, of course. And you may feel that you know exactly what one or many of these concepts are. And you may actually prove me wrong in a very simple way. So I'm happy to invite people to give me feedback and to contribute comments and suggestions to this course. And a way to do that is just to make comments on the videos themselves. So for example, if you know how to define what a function is, for example, then you can prove me wrong once and for all just by laying out very clearly for us what exactly a function is. But you must be aware that I have pretty stringent demands on a definition. If you're going to use a definition with 4 or 5 key mathematical words involved in it, you had better make sure that those 4 or 5 mathematical words have some prior definition somewhere. That there's some link, essentially, from those words to some other place where I can find out what you mean by those words. So for example, with the idea of a function, if you tell us that, well, a function is a rule that takes an object of one kind and outputs an object of another kind, obviously I'm going to ask you, well, what do you mean by the word rule? Yes, you can define function in terms of rule, but you probably also could define rule in terms of function. And we want to make sure that we don't have that kind of circularity in our definitions. So if you're going to define function in terms of rule, please make sure that somewhere you have a good definition of what a rule is. Okay, and that goes for any possible definition that you're going to make. We have high standards in this course, and appeals to authority are not going to carry very much weight for us. Okay? It's scientific evidence, scientific clear thinking, which is going to carry the day or not. So does any of this matter? Who cares if modern mathematics has lots of definitions that don't really work, or if people are fast and loose with rigor? Does it really make a difference? Well, I think it does. It makes a lot of difference, and it has a lot of consequences. And the first and foremost consequence is the difficulties with mathematics education that are a direct consequence of these logical weaknesses. We all know that mathematics education in the modern world has some serious problems. And there's a range of possible reasons, and people debate and discuss what the problems are, how to fix them. In my opinion, a very serious contributor to this problem is the fact that pure mathematicians have not figured out their subject in the right way. This is a key aspect of the problem. If us pure mathematicians understood our subject properly, with an absolutely clear logical structure, then it would have enormous repercussions for mathematics education. In particular, teacher training is made a lot easier with logical, clear mathematics. Developing curriculum is dramatically simplified if you have a strong understanding of the logical flow of the subject. Student motivation is easier to capture if the mathematics makes sense. These niggling problems of logical inconsistencies are not invisible to younger students. They may not be able to put their finger on it, but they can smell that things don't work. They can sense that they are not being given a logically tight subject. And I think a lot of them are turned off of mathematics because of the prescriptive nature. Memorize this and memorize that, and don't argue with us. Do mathematics in the right way and it becomes simpler. If you want an example of that, learn about rational trigonometry. Rational trigonometry is a new and much simpler way of doing trigonometry, leads to a much simpler way of doing geometry, and it's because you approach the subject in the right way, so then it becomes a lot simpler. And when people do eventually move to rational trigonometry training in schools, the result will inevitably be much happier students and teachers. That's just one example, but it's a very good example. Another consequence of the logical weakness of modern mathematics is the convoluted and overly complicated research that's going on. Our journals are full of convoluted and overly complicated stuff. And it's unfortunate. And to a certain extent, it means a waste of the energies and the efforts of a whole generation of researchers. Okay, so there's a lot to be gained by putting mathematics back on the right track. And finally, another important consequence is that we end up having inappropriate and ineffective tools to give to the applied mathematicians. The physicists, the computer scientists, the statisticians, and others, they want pure mathematical theories that will fit the problems that they're trying to investigate. And our best chance of giving them the right tools is to understand mathematics in the right way. And that absolutely requires a logical understanding of the subject. It's got to make logical sense, and if it doesn't, you can be sure that it's not the right way of thinking about mathematics. So in this second part of the course, my aims are to, first of all, provide a careful, honest, and clear overview of the problems with modern pure mathematics. And I want to look in detail at the critical issues. So we're going to have a very, very good and thorough look at a lot of the problematic issues. So it's not going to be entirely negative, because we are going to be learning a lot of things while we're doing this. Okay, so it's still going to be very much a learning experience. I hope that you're going to learn something with each video. For example, we're going to have a very in-depth discussion of real numbers and all the different possible approaches to real numbers. And I'm going to explain to you why none of those approaches work. Okay, so you're going to learn something from that. We're going to talk about infinite sets, limits, integrals, many things in some detail. So even if you're not too familiar with some of these ideas, you will become familiar with them at the same time as recognizing where the logical problems are. And ultimately, I want to do something positive. What I want to do is I want to lay the groundwork for a new and improved and simplified approach to, well, at least certainly calculus and analysis. So I'm going to be aiming towards this algebraic calculus, which I've already told you a little bit about. but we are going to be aiming towards establishing that on a very proper footing. And finally, I want to reorient a new generation of mathematics students. I'm very conscious of all those students of mathematics out there who are currently being offered what is, in my view, an inadequate theory. And I want to fix that situation. I want to give them something which is better than what's currently on offer. And the students can be young or old or in between. The important thing is to have a flexible approach, to have an open mind. And that's going to be very important in this part of the course. So I ask you, as members of the jury, not to decide too soon. Listen to the evidence, weigh it carefully, and try to make up your own mind. It's an interesting challenge to be confronted with ideas which are contrary to the way we've been trained to think. It can be disorienting. And our initial reaction, of course, is to try to reject that kind of thinking. But if we are wrong and we can admit to it and change our orientation, it can be a very positive thing for us. So I hope that in the fullness of time you will appreciate this new way of approaching mathematics that I'm going to lay out for you. All right, so the trial begins. With our next video, we are going to look at rigor in modern mathematics and why it's at such an unhappy state. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.